Okay, good morning. Okay, so let's start. Okay, so today we will be having a very rough or very brief discussion of the remaining parts of mathematical induction. So let me see. Okay, so let me enter the full screen here. Now, so in this set of lectures, so we have started by showing a particular induction form, the basic induction form, and now we have something called the strong induction. So for strong induction, we have the basis case is still the same. We need to show some statement like P1 is true, but then after that, the inductive case, we are going to show something a little bit different. We want to show that for all n, if we know that P1, P2, P3 up to Pn, they are all true, then we must have Pn plus 1 to be true. Now notice that if we can somehow show that this is correct, then the induction process still work, because if we now have P1 known to be true, together with this one says P1 implies P2, so we will know that P2 will also be true. And now we have P1, P2 both true, and by using this again, because this one says if P1, P2 are true, then we must have P3, so we can then show that P3 is also true. And again, now we have P1, P2, P3 known to be true, so that we can apply this one again and show that P4 is also true. So we see that by just showing that P1 is true and also this sentence, then we can actually show P1 is true, we can then show P2 is true, we can then show P3 is true, and for every n, we know that Pn has to be true. Okay, so strong induction and the original induction. Original induction, we don't have a lot of things. We just have P1 is true, and then if Pn is true, then Pn plus 1 is true. So both of them can do the same thing, can show every case Pn will be true. But then strong induction is actually more easily to be applied. The reason is that because we now have more information that we can assume when we are trying to show Pn plus 1 is correct. Previously, we just know Pn is correct. And originally, without anything, without the induction process, we don't know anything, and we just want to, and we need to blindly show Pn plus 1 is true. But now, in the basic induction case, we have Pn assumed to be true, so that we have an easier task to show Pn plus 1 to be true. And now with strong induction, we have even more information. So we can assume all these P1, P2, P3 up to Pn, they are true. And then under this assumption, we can show Pn plus 1 to be true. And it will be much easier. So in the lecture notes, we have a couple of examples. The first one is we study the Fibonacci numbers. So Fibonacci numbers are defined such that we have the first two terms to be 1 and 1. And then for every term after that, a particular term is equal to the sum of the previous two terms. So we have 1, 1, and then we get 2. And because of 1, 2, we get 3. Because of 2, 3, we get 5. So we have this sequence. This sequence of numbers have a lot of interesting properties. So in particular, we want to show this. We want to show that a particular term Fn can be computed by using the formula, something like this. Let me see. Let's see if it is correct. Yeah, sometimes I make a mistake with the power here. So let's see. If n is equal to 0, then what will happen? If n is equal to 0, then we will have 0. So actually, my formula here is slightly wrong. So here it is, instead of n here and instead of n here, I think it should be n plus 1. But never mind. So we somehow, in our example, we want to show that Fn can be expressed by something, we call it a closed form. Just plug in the value of n, and then we can compute it. So how do we show this? So to show this, we are going to show two basis cases, because there are two cases that doesn't have any information. We want to show F0 is correct, and we want to show F1 is correct. And after that, assuming that P1 and P2 and P3 up to Pn, they are all correct, then we want to show that Pn plus 1 is also true. So we want to show that this is the case when n is greater than or equal to. So we want to show something like this in general. Okay. So check out the OCW recordings and see how to do so. It will not be very difficult. Okay. The next example here is we introduce a sorting algorithm called quicksort. So sorting algorithm do what? It gives us a collection of numbers, and then we want to arrange them from small to large. And the quicksort method, the quicksort algorithm works like this. Okay, so if our collection just have one number, then we are done. Okay, we just return it. But on the other hand, if our collection of numbers, there are more than one, then we pick one of them. We pick one of them randomly, okay, whichever. Based on the selected number, let's call it x. And we can use this x to divide the collection into two groups. One part containing the numbers that are smaller than x, and then the other part, there are numbers that is larger than x. So in that case, after doing this process, we will have two groups which has smaller size, strictly smaller size, because x is now taken away. What we want to do here is that we want to apply the same method to work on the smaller sets, the smaller collection, and also we want to apply the same method on the larger collection. Okay, somehow, after it is done, then hopefully we should have a sorted collection of the smaller numbers, and then we output this, and then we output x, and then we output the sorted collection of large numbers afterwards. Okay, so this is the idea. So for instance, so suppose that we have the collection 1, 4, 3, 10, 7, 2, and suppose that we pick 3. Now by picking 3, we look at each number, compare it with 3, so we find out that 1 and 2 are the numbers that are smaller, and then 4, 10, 7 are the numbers that are larger. So somehow magically, we apply quicksort on each group, and then we have the resulting part of quicksort of S put here, and then put x here, and then we put the resulting part of quicksort of L there. Okay, now we didn't go through the whole process now, but we want to argue that quicksort can always correctly sort any collection of n distinct numbers. So why is it true? So we can simply show this by induction. So notice that the process here, the quicksort process, is called a recursive algorithm. Recursive means we are using the same thing again and again. So quicksort here, an important part of quicksort is the running of quicksort will require quicksort itself. But of course, we are not doing the same collection of numbers. We are doing a smaller set of numbers, a smaller collection of numbers. So quicksort will rely on quicksort. So this is called a recursive algorithm. So usually the correctness of a recursive algorithm, why a recursive algorithm is correct, can usually be proven using induction. So here we will see that quicksort can correctly sort 0 numbers or 1 number, right? So assume this is true, and assume that quicksort can sort any collection of numbers from 1 number, 2 number, up to n numbers. Okay. And so by using the strong induction argument, we are trying to show that suppose that quicksort can sort 0 numbers, 1 number, 2 numbers, up to n numbers correctly. Then we can use quicksort to sort n plus 1 numbers. Now the idea is very simple. To show this, when we are sorting n plus 1 numbers, so quicksort will isolate a particular number, let's call it x, and divide the remaining numbers into 2 groups, so that the 2 groups will have size at most n. So this set of S will have at most n numbers. This collection of L will have at most n numbers. And because we have the induction assumption that if the total numbers is less than or equal to n, then quicksort will work correctly. So in that case, quicksort of S will correctly sort the smaller group of numbers, we put it here, and then we put x. X is one that is in the middle, and we put the collection of correctly sorted number of L here. So in that case, it must be an increasing sequence containing all the numbers. So in that case, quicksort is correct. Okay. And then we have also discussed a game. This game is called the Peg Solitaire. So we assume that we are using a two-dimensional board. So let's say the board has infinite, size. Okay, so I just focus on a very small part here, but actually you can assume that there are still more squares here, more squares here, more squares here. And I want to tell you the rule of this Peg Solitaire game. So the game is like this. When you see an empty square, and then you see two adjacent nodes, that is like so that is if you see an empty square and you see an occupied peg adjacent to it, and also another occupied peg in the same direction, again connected or adjacent to this one, so something like this, we can perform some action called jumping. So we can jump this piece to the empty position. So by jumping, the middle one is now being eaten or taken away. So after jumping, we will have this situation. So perhaps we can also do a jumping like this. So if we jump this one to this one, then these two are no longer contained any pegs, but then this one is now moved to here. The question here is that if I have a beginning board with some pegs on it, can we use a sequence of movements such that the board will just have exactly one peg left? And so in this particular example, we want to show that the beginning board will have pegs, will have n square pegs. They are arranged as a square in n by n, in an n by n region. And then we assume that this n is not divisible by 3. We want to show that in this case, we can eliminate all but one peg. So in the OCW recording, we have explained why this is true. So 1 by 1 is simple, right? 1 by 1. So if we have just one peg, is done. 2 by 2. So forget about these two, forget about these two. So how we can do so? So we jump this one to the above, we jump this one to the above, and then we jump this one to the left, something like this. So we will have exactly one peg left. So we want to show that when n is 1, 2, 4, 5, 7, 8, 10, 11, as long as n is not a multiple of 3, then this can be always done. Okay. And then the induction case is a little bit interesting. It's not strong induction. It's not the natural weak induction that we have. But somehow, we can show that if we can solve the case for 3n plus 1, then we can solve the case for 3n plus 5. And also, we can show that if we can show, we can also show that if 3n plus 2 can be solved, then 3n plus 4 can be solved. So by just having this part, and together with the condition P1 and P2 are true, so that we can solve for the case of 1 by 1, we can solve for the case of 2 by 2, then every cases that we want can be shown to be correct. Reason, because 1 is correct. 1 is of the form of 3n plus 1, right? By plugging n is 0. So 1 is of this form. So 1 implies 5. 2 is here, and 2 implies 4. So because 1, 2 are correct, we know 4, 5, they are also correct. Now how about 4? Now 4 is of the form here when n is plugged in as 1. So 4 implies 8, while 5 implies 7. So because 4 and 5 are correct, then we have 7 and 8 are correct. And now we have 7 and 8. Now because 8, for 7 belongs to here, so that by plugging n is equal to 2, 7 gives us a result here. 7 implies the case of 11, while 8 implies the case of 10. So because 7 and 8 are correct, we know the cases for 10 and 11 are correct, and so on and so forth. So by doing this induction process, we can show that for every n such that it is not a multiple of 3, then we can always solve it. Okay. Now finally, we have this slide. So we can easily jump in. So if we are not familiar or if we are not very careful about induction, we can create some silly mistakes and then give us some silly results. Okay, so here, for instance, we want to show that if I have a collection of n cats, any n cats, then they must have the same color. So I want to show something like this for every n. Now, obviously, this is wrong. You can show that this is wrong by giving us a counterexample. Just pick up two cats. One of them is white and the other is black. Then it is wrong. They don't have the same color. But somehow, your friend who has just learned induction gives you this proof. Your friend says, okay, so he gives you a proof, and your purpose is to answer why this proof is wrong, rather than showing that this statement is wrong. Okay, so you need to find out the mistake inside the proof, rather than giving an alternative counterexample to show that whether the statement is right or wrong, it doesn't matter now. You want to explain to your friend why his or her proof is wrong. So let's see the proof, the wrong proof. So the proof says the basic step P1 is true. No, so P1, what is P1? P1 says any one cat will have the same color. Okay, that's correct, right? Any one cat must have the same color. Yeah, just one cat. Now the next sentence says, assume that PK is true. So assume that any K cats will have the same color. Then we have K. So let's consider how we can show PK plus 1 to be true soon. Okay. So to show PK plus 1 to be true, let's consider the case where we have we have K plus 1 cats. Okay. Now if we have K plus 1 cats, then what can we do? Let's remove one of them. Let's call it Y, so that the remaining part will just have K cats and they have to be of the same color. So what does that mean? So we have K plus 1 cats. We take away one of the cats, we call it Y. So what does that mean? The remaining part will just have K cats. So in that case what? In that case, they must be of the same color. And now what after next is we find a cat here, and then we switch it with Y. So after switching, so Y is now back. When we switch it with Y, then we will have what? We will have this cat out and then Y inside. Now again, this group of cats, they are just K cats. So we assume that PK is true, so they must all be of the same color. Okay, so what does that mean? So these cats have the same color. Y is also of the same color, so everyone is of the same color. So we have now just shown that all the cats are of the same color. Okay, so there must be something wrong in the proof. So what's wrong? Okay, so I'll leave you to think about this. So I think in the OCW recording, it is fully explained. But if you have not watched the video yet, yeah, go and try and see if you can pick up the mistakes here. Okay, so we have a rather short lecture summary today because we don't have much slides to cover. So in the lecture notes or in the recording, we have also talked about some more interesting examples. So you may want to check it out when you have time. So next Monday, we will have our exam 1, so we won't have a tutorial on that day. So let's meet again next Wednesday, where we will have our lecture summary again. Okay, so let me check if there are any questions here. Let me check. Okay. Okay, good. So far, so good. So I don't see any questions here so far. So, okay, so let's end the class today. And then if you have any questions, yeah, please ask us. Or if you don't see our response very quickly, yeah, send us email directly to our mail account. Okay? Okay, good luck to the exam. See you next week. Bye-bye.